In this final section of this chapter, we will discuss a special family of infinitely divisible distributions, the so-called alpha-stable distributions, and their associated Lévy processes. Okay, so let's begin with the definition. Okay, so alpha-stable distributions are defined for this parameter alpha strictly in between 0 and 2, and they are defined in terms of their characteristic function. Now, the characteristic function will be of the form that we proved in the last section, with some specific choice of the Lévy measure. Okay, so the measure mu here is defined through this density px. So in this representation we have, as usual, this constant gamma, and the measure mu is defined by this density, where the density must be of the following form. Okay, for some non-negative constants m1, m2. In other words, the density is of the form 1 over the absolute value of x to the power 1 plus alpha, but on the positive half line and on the negative half line it can be scaled by a different constant. And notice that compared to the general representation of infinitely divisible characteristic functions, the Gaussian term here is excluded. So in this representation, sigma squared is equal to 0. First of all, let's notice that this choice of alpha between 0 and 2, it just corresponds to the condition that the integral of x squared truncated at 1 of the Lévy measure mu should be finite. Right, so since the density of this measure blows up at 0 as 1 over x to the 1 plus alpha, this scaling by x squared near 0 will make this into an integrable function exactly when alpha is in between 0 and 2. And then a special case in this definition, when the constant gamma is 0 and the constants m1 and m2 are equal, is called symmetric alpha stable. Now, one can actually compute the integral in the above definition explicitly. Okay, but in this section we will mostly focus on the symmetric case, so let's compute the integral in the symmetric case. So namely, in the symmetric case, the integral is of this form, but we can see that by symmetry the complex part of this integrand will actually be 0. So we are only left with the real part, which will be given by the following integral. But if we make the change of variables in this integral y equals to tx, then we can see that it can be rewritten as follows. So this factor t will just come out from the integral as a power alpha of its absolute value, and then we'll be left with the integral that does not depend on t, okay, namely the following integral. And we can see that this is just minus some positive constant times the absolute value of t to the power alpha. So in other words, a characteristic function of a symmetric alpha stable distribution is given by the exponential minus some positive constant, the absolute value of t to the alpha. Okay, so it takes this particularly simple form. Now, the reason these distributions are called stable is because they satisfy the following stability property. Namely, if random variables x and then x1 up to xn are IID alpha stable, then the sum of random variables x1, xn has the same distribution as random variable x rescaled by n to the power 1 over alpha and some possible shift by a constant. Okay, where this constant k of course depends on n and on the parameters of the distribution, but in the case where we have a symmetric distribution or symmetric alpha stable, so when gamma is 0 and m1 is equal to m2, then this constant is actually 0. Okay, and so we can see that these distributions satisfy a stability property very similar to the Gaussian. Okay, the Gaussian would correspond to the case alpha equal to 2, where rescaling by square root of n gives you the same distribution, whereas here you rescale by n to the power 1 over alpha. Now, in the symmetric case, this is completely clear because the characteristic function is of this form, and so if you take a sum of IIDs, the characteristic function will be just multiplied by n here in the exponent, right? But if you rewrite it by just rescaling your t, then this is clearly just a characteristic function of one such x rescaled by n to the 1 over alpha. And so this shows the claim in the case of symmetric alpha stable, but the general case is essentially identical. That if you consider your characteristic function and just see what happens when you rescale your random variable by a constant, right? This corresponds to rescaling t by the same constant. Okay, now I'm just going to write the part inside the exponential. So if you rescale t by some constant, let's say a, then you will have this constant term like this and the same integral with t rescaled by a. And then first, if you make the same change of variables as above, y equals to ax in this integral, okay, then this constant will just come out as before to the power alpha. Right? That's because density p was of the form 1 over absolute value of x to the 1 plus alpha. And so the integral that you're left with will be as follows. So essentially the same integral, just the indicator is between minus a and a. But if you replace that indicator by the indicator that we want, namely between minus 1 and 1, okay, then the difference between the two integrals is of the form I times t times some constant. So it will simply redefine the constant in the first term, so I'll write it as L. But of course you can write explicitly what this L is in terms of all the parameters here. And then we see that if we take this constant to be exactly n to the 1 over alpha, then this factor will be just n, and so this characteristic function can be written as the nth power of characteristic functions of exactly the same form, so corresponding to the same alpha stable distributions. Right, just the constant will be redefined, and that corresponds exactly to that constant shift in the statement. Okay, but otherwise this finishes the proof. Next, we are going to give an explicit construction of alpha stable random variables in terms of sums over Poisson processes. But first we will discuss a slightly simpler object, the so-called subordinator processes. So these processes are defined as follows. So first we consider phi to be a Poisson point process with the mean measure given by the product measure d mu on the coordinate x and the Lebesgue measure dy on the second coordinate y, and we consider this process on 0 infinity squared. So in other words, both coordinates x and y here are on the positive half line. And this measure mu is such that the integral of x truncated at 1 with respect to this measure on 0 infinity is finite. Then the process tau of t for non-negative t of the following form, where we sum x over all points such that the second coordinate is less than or equal than t. Okay, and the sum is over all points in this Poisson process defined above. Okay, the process of this form is called a subordinator. Okay, first let's notice that this process is well defined because by Campbell's theorem, the sum over a Poisson process of some function will be well defined when if the integral of the minimum between this function and 1, so here the function is x times indicator that y is less than or equal than t, with respect to the mean measure of the process is finite. But of course here the minimum will be 0 if y is greater than t. So we integrate with respect to dy only on the interval from 0 to t. So that results in t, and then we are left with the integral of the minimum between x and 1 with respect to the measure mu. And by our assumption this is finite, so by Campbell's theorem the sum above is well defined. Now, just by definition of this process tau, we can clearly see that it's non-decreasing in t and right continuous, simply because the inequality in the indicator is non-strict. Then we can see that the increments are independent. Right? That's because if we take any two times t and s, then we can write the increment as a sum of x over the interval s and t. And we can see that this sum is expressed in terms of the points in our Poisson process on the set 0 infinity times this interval from s to t. And when these sets are disjoint, just by our properties of Poisson processes, those sums will be independent. And we can also see that our process tau is stationary, and that's because the Debye measure dy is translation invariant. Right, so in the sum for the increment, it doesn't matter where this interval from s to t is, as long as it has the same length, you will get the same distribution. And finally, of course, it's continuous in probability, because as we said, the process is right continuous, so when you look at the increment of your process, right, it will go to 0 when c goes to 0. In other words, any subordinator is a Lévy process, and in fact it's a non-negative Lévy process. But because we know that a Lévy process is determined by the distribution of the process at time 1, and because we also know that any infinitely divisible random variable can be given as a sum over Poisson process, this means that all non-negative Lévy processes are subordinators. Now, to visualize how this process looks like, let's just restrict ourselves to the interval from 0 to 1. Okay, and the reason because on this interval, the Debye measure dy is a probability. And so this process can be viewed alternatively as follows. So first we can consider a Poisson point process pi with the mean measure mu on the positive half line. And then for every point x in this process, we can take yx to be a uniform marking on 0, 1. And of course, by marking theorem, we know that the set of these points x with its markings for all x in this Poisson process on the positive half line, it's the same object as the process that we defined above, with the mean measure just given by the product on the product of half line with interval 0, 1. But in this point of view, we can write the subordinator process as the sum over all points x from this Poisson point process on the positive half line, x times the indicator that its marking is less than or equal than t. Okay, where again these markings are IID uniform random variables on 0, 1. And we can see that in this definition, this process here has a jump x at every point t given by its marking yx. And so if the measure mu is finite, then we have just a finite Poisson number of points, and so we have a finite number of jumps here. But if the measure mu of the half line is infinite, then of course it means that the cardinality of this process is countably infinite. And so this set of times where you jump, which are IID on 0, 1, of course it will be a dense set on 0, 1 with probability 1. Okay, so in this case you have this dense set given by these IID uniform random variables on 0, 1, and at every point you jump by the corresponding value x coming from this Poisson point process on the positive half line. And then within this family of subordinator processes, we will consider a special case of the so-called Zeta-stable subordinators. Okay, which is just a subordinator process as above, corresponding to the measure mu of the following form. On the positive half line, where a parameter zeta is between 0 and 1, and the constant c is some positive constant. And so in order to understand how these zeta-stable subordinators can be used to construct alpha-stable random variables, let's compute the Laplace transform of such a subordinator using Campbell's theorem. Okay, so we recall that by Campbell's theorem again, if we want to compute a Laplace transform for some positive parameter lambda of this process at time t, okay, so here, since t is already reserved for time, I take the parameter in the Laplace transform to be lambda. By Campbell's theorem, we know that this is the exponential of minus the integral with respect to the mean measure of the process. Okay, so here it will be a double integral because our mean measure is a product of 1 minus e to the minus lambda times the function that we sum. Again, here recall we sum the function x times the indicator that y is less than or equal than t. And then the mean measure is c x minus 1 minus zeta dx dy. And then again we notice that the indicator that y is less than t will be 0 when y is greater than t, and in that case the integrand is 0, and so the integral in y is only on the interval from 0 to t. So as a result, that will just give us a factor t in front of the integral with respect to x only. Right? And then we consider when the indicator is equal to 1. And then finally, making by now the usual change of variables, y equals to lambda x, we can see that this integral can be rewritten as Now let me also take the constant c outside of the integral, and then the parameter lambda will again come out with the power zeta here, and we'll be left with the integral of 1 minus e to the minus y to the minus 1 minus zeta dy. Okay, so this final integral is just some constant that depends on zeta, so the Laplace transform will be of the form minus ct lambda to the power zeta times some constant, let's say a of zeta, given by the above integral. But the main thing to notice here is this dependence on the parameter lambda in this Laplace transform, right? The dependence is of the form lambda to the power zeta, which very much resembles the form of the characteristic function for the alpha stable distribution, specifically for the symmetric alpha stable distribution. And as a result, one can construct alpha stable random variables in terms of this zeta stable subordinator as follows. Let Wt be a Brownian motion independent of our subordinator process tau. So this independence, of course, assumes that they are defined on the same probability space. Okay, and then let's consider the following time change of the Brownian motion, namely the Brownian motion at the time given by the subordinator process. And now, if we compute a characteristic function of this random variable, now first let's compute it conditionally on the subordinator time tau. Now, because w is just a Gaussian random variable with variance equal to this time tau, the conditional expectation will be just the usual Gaussian characteristic function. So we get minus x squared, the variance is tau, divided by 2. But this is now a Laplace transform of this subordinator tau with the parameter x squared over 2. So if we plug this into the above formula, we get an exponential of the following form. And here we recognize that this is a characteristic function of a symmetric alpha stable distribution with alpha equal to 2 zeta. Moreover, one can check that as a function of time t, this process w tau t is the Lévy process corresponding to this alpha stable distribution. Namely, one can check that the increments are independent and stationary, but we will leave this as an exercise at the end of this section. Now we can also notice here that when the subordinator tau jumps at some time t, our Brownian motion jumps. So the increment of the process at that point is just the increment of the Brownian motion given by that jump. And since the increments of the Brownian motion are independent Gaussian with the variance given by the jump, we can also define this process, this alpha stable Lévy process, without using a Brownian motion. Okay, instead we can just use the markings given by Gaussian random variables with the appropriate variance. So more precisely, okay, given our Poisson point process as above, so point process with two coordinates x and y, and with the mean measure of this form on x and Lebesgue measure on y. And then for each point in this process, we can consider a marking, let's call it G, with conditional distribution given by the Gaussian with the variance given by x. So because the jump is x, we want that to be the variance of the Gaussian. Okay, and then we can define some process xt to be simply the sum over all points xy in this Poisson point process. But instead of jump given by x, we sum the marking g, okay, which of course depends on the point xy. In this definition, although the distribution depends only on x, and then the indicator that y is less than or equal than t. Now we also know that the process x, y, g, by a marking theorem, it's a Poisson process on 3 coordinates. And so if we like, we can erase here the dependence of g on the point and just view it as another coordinate in the Poisson point process on 3-dimensional space. And so in other words, this is just a sum over a Poisson process again, and so we can check by Campbell's theorem directly that it satisfies all the properties that we want. And so we will leave this as another exercise to check that this gives us a Lévy process corresponding to the alpha stable distribution. And so in other words, we gave some concrete construction of these alpha stable random variables and their corresponding Lévy processes in terms of sums over Poisson processes. And this finishes this section, and also this wraps up the chapter on Poisson processes.